Okay, let's continue this video. I want to continue drawing Bohr's model a little bit further, and I want you to understand why elements can have a certain charge to them. Charge meaning that I'm either going to want to give up an electron or I'm going to want to take an electron in, okay? Now, with these valence electrons, I want to let's look at sodium. So sodium, for example, is in the, which row? Third. So I know it's in the third row, so I'm going to draw 3 rings around the nucleus. So I have 1, 2, 3. So here's my 3 rings around sodium nucleus. And the first ring, I know that's the first row of the periodic table, so how many electrons can be on the first ring? 2. So I'm going to draw 2 electrons around that very first ring. On the second row, or the second energy level, because we're saying those mean the same thing, there are 8 elements in that second row, so there must be 8 electrons on that row, or on that ring. So let's draw 8 electrons. Okay. So I have 2 on the first ring, I have 8 on the second ring. Now I'm on the third ring. I know that the third ring can hold a maximum of 8 electrons, but I'm at the very first element of those 8, so that means that sodium is only going to have 1 electron on its outermost shell. So it looks like this. Okay, I now would like you to, I want to draw the Bohr model for neon. I want to draw this Bohr model for neon. So I know neon is in the second row of the periodic table. And I know that if it's in the second row, it should have 2 rings around the nucleus. So I have 1, I have 2. So 2 rings. 1, 2. The first ring should have how many electrons? You know that. It should have 2. Why? Because there are 2 elements in that first row. Second row, 8 elements in the second row. It is the 8th element in that row, so it should have 8 electrons on its shell. 1, 2, 3, 4. Okay. So I have this. So I have 2 electrons here. I have 8 electrons on that ring. Now, can that second ring hold any more electrons? You should be saying no. That ring can only hold a maximum amount of 8 electrons. It is full. It has 2 in its first ring, which means that it's full. It has 8 in its second ring, which means that it is full. So because both of those rings are full, it is very stable. And it's because it doesn't need any more electrons to have a full shell. It has a full shell. I want you to look now at that sodium one that you drew. So for this third shell to become stable, it needs 8 electrons on this outermost shell. So to do that, it would have to gain 7 electrons from something else to become stable. It does not want to do that. Gaining 7 electrons is a lot of work. Another way that sodium could get a full shell, or full outer shell, if it gives away this electron, this whole ring goes away, and it's left with just 2 rings that are full. So sodium wants to give up this electron because it's so much less work than having to gain 7. So I want you to think about it. Is it easier to give up 1 electron, or is it easier to gain 7 electrons? Now, you know, as a student, you want to do the least amount of work that is possible. So do these elements. Sodium does not want to give more energy than it needs to, just like you don't want to give as much energy as you may need to. So sodium would give away this 1 electron. It wants to go away. If it gives 1 electron away. So right now, I want to draw, or I want to write how many protons and electrons this one has. Let's write how many it has before we take this electron away. Okay, so sodium, if we look on the periodic table, just the way that it's written, has an atomic number of 11. So I know that it has 11 protons, and if it's neutral, it's going to have 11 electrons. So this is what I have. Has 11 protons, 11 electrons. If sodium gives that one electron away, then that changes my electron count from 11 to 10. So just like what you did on your homework before with that basic atomic structure, you know that now I have one more proton than I have an electron. And if that's the case, since I have one more positive charge than I do a negative charge, sodium will end up having a +1 charge. So sodium ends up having a +1 charge. Since it gave this electron away, this is what the Bohr's model for sodium will now look like. This is the way that atoms will bond, and this is the way that bonds can work. They can give electrons away, they can share these electrons through their shells. So if you look at the slideshow, I showed you sodium and chlorine, and I showed you how sodium wants to lose that one electron, and chlorine wants to gain one electron to have a full outer shell. So you'll see then that sodium here becomes positively charged, chlorine becomes negatively charged. Tomorrow in class I'm going to do some more examples with you about those. So whatever questions you have about these, bring them to class on Monday, okay? So I want to keep going though through these families because we're just going to go through them pretty quickly. So the next family or group or column on the periodic table are the alkaline earth metals. Now, just like the alkali metals, these alkaline earth metals are never found by themselves in nature. They're always bonded with something else. And they have 2 valence electrons, so that just means that on that outer ring on Bohr's model, they have 2 electrons on that outer shell. Okay, now they are pretty reactive, but they are not anywhere near as reactive as the alkali metals are. Now the next big family or group that we're going to talk about are the transition metals, and that makes up this entire block. So it's this entire block on your periodic table. On the periodic table, there are elements that are considered to be A elements, and then elements that are considered to be B elements. All of the transition metals are considered to be B elements, and we'll talk more about that tomorrow. A elements just mean representative elements, so it means that a lot of them have a lot of different properties, whereas B elements, all of the transition metals have very similar properties. So with this it says that these transition metals are probably the metals that you're most familiar with. We have copper, there's zinc, there's iron, there's nickel, there's gold, there's silver. That's what you're used to. You're used to hearing about those. Transition metals are pretty good conductors of heat and electricity, but what's really cool about transition metals are that in reactions they can give off some really neat colors, and it's because their outermost shells, when you draw their Bohr model, they can be very different. And that's why we don't ever draw the Bohr model for them, because some of them can have multiple charges, and it just depends on the case in which they're bonded with, or the way that you find them in nature. So the next family is the boron family. I do not care necessarily that you know about this at all. So the boron family is just because boron is the very first one in that column, so they call it the boron family. And pretty much all you need to know is that this family includes aluminum, which is definitely one of the most abundant metals in Earth's crust. The carbon family is another family that I don't necessarily care that you know about. On the carbon family, it has 4 valence electrons on its outermost shell, and again, we're going to draw more of those tomorrow in class. The next family is the nitrogen family. The nitrogen family has 5 valence electrons on its outermost shell. The next family is the oxygen family. That family has 6 valence electrons on its outermost shell. Now, this family I do want you to know about. So right now the families that I care most about are alkali metals, alkaline earth metals, transition metals, and now this halogen family. So far there are 4 families that I will quiz you on or test you on, okay? The halogens. The halogens have 7 valence electrons. And I want to draw, actually, let's draw one of the Bohr models for those so that way we can see that it has 7 valence electrons. So let's do fluorine. Okay, fluorine is in the second row. So how many rings should it have around the nucleus? It should have 2. So I'm going to draw 2 rings around the nucleus. In the first ring, it should have 2 electrons because they're 2 elements. In the second ring, or on the second ring, it can have a maximum of 8, but fluorine is the 7th in that row, so it should only have 7 electrons around its second ring. Okay, it's going to look like that. So I have 1, 2, 3, 4, 5, 6, 7. So I have 7 valence electrons there. So again, valence electrons just meaning the electrons that are on that outermost ring. So I know that I have 7 out here. If fluorine gained 1 more electron, it would be stable. It would be acting like it was neon, because then it would have 8 valence electrons on that outermost ring. So for fluorine, would fluorine rather gain 1 electron, or would it rather give up 7 electrons to have a full shell? It would rather gain 1. Again, it takes much less energy to gain 1 than it does to get rid of 7. So if fluorine gained 1 more electron, it would be stable. As of right now, fluorine has 9 protons, and as of right now, it has 9 electrons. So I have 9 protons, 9 electrons. It's stable. Sorry, not stable. It wants to be stable. It can be stable if it gets 1 more electron. So let's say that fluorine does gain an electron. Let's say we add an electron. I added that little electron here. It adds this electron. It has 8 electrons now on its outside shell. It has 9 protons still because I didn't change anything about the nucleus. But now it has 10 electrons. So if I wanted to write the charge for fluorine on this, I would say that because it has an extra 1 negative charge, so I have 1 more negative charge than I do positive, fluorine will have, or wants to have, a -1 charge, okay? That means that all of these elements in the halogen family or halogen group want to have a -1 charge because all of them has 7 valence electrons. Okay, very last, one of the last families, I guess I should say, on the periodic table are the noble gases, and that is this column right here. Okay, on these noble gases, these noble gases are unreactive, and they are colorless, and they are very, very, very stable. All of the elements want to behave or want to get a shell with 8 electrons on the outside of it, so that way they can, at least in the second or third row, I should say, so that way they can be happy, they can be stable, their shells can be full. Now, noble gas can also be called, or this family can also be called inert gases. And all that means is, inert means that they're just unreactive. And they're unreactive because they don't need to gain electrons. They don't need to lose electrons. They're going to hold on to the electrons that they have very tightly because their shells are full. So they don't need to react with anything. They don't need to bond with anything because they're already stable the way that they are. The very last 2 on the periodic table are the ones that are on the bottom. So these 2. And those are the lanthanides and the actinides. Now, typically these are the ones that are synthetic, which just means that they're man-made. Now, not all of them are synthetic, not all of them are man-made, but for the most part they are. And you know also that on your periodic table, the lanthanide